today I'll be talking about how physics and its principles are in connection with architecture, and why buildings are built the way they are, and what architects have to think about before actually designing them. Now, one aspect that I will be talking about is the Bernoulli's principle. Does anybody have any idea what is Bernoulli's principle or what it consists of? Yes, sir.
Does that have to do with pressures and area?
Exactly. Now, as you said with the area, it's just like how you're in a bigger, site, and the pressure of that site is going to be larger, making the velocity of the wind smaller. Now, if you're in a smaller site, there's going to be less pressure, but the velocity of the wind is going to be faster, creating a system through a site rather than a barrier and causing stress on the buildings. Now, anybody else? Yes, madam.
Do you have any prime examples of Bernoulli's principle?
Well, one prime example is the Canary Wharf. It is a business district built entirely on water in London, England. Now, I'm going to be using this site particularly to show the Bernoulli's principle and how the wind effects goes through the system. Now, as the northwest wind comes through the system onto the site, the aerodynamic shapes of this building goes through, creating a system rather than a barrier of these buildings and causing stress. Now, as I said before, the larger the area in this courtyard, the larger the pressure, making the velocity smaller. And through these crannies, the velocity is going to be larger because the area, the cross-sectional area, is going to be smaller. And that is the Bernoulli's principle pertaining to this particular site, Canary Wharf, located in London.
And now, a quick intermission of the equations of Bernoulli's principle. Bernoulli's principle states that a total energy is a steadily flowing fluid system that is constant along the fluid path. If we apply the law of conservation of energy and substitute the formulas, we can divide both sides by volume, or V. Now that V is distributed on both sides of the equation, we can say that V is a constant. Looking at the formula, we can see density is equal to mass over volume. We can now rewrite the equation as
Hello, mate. I'm back again talking about fluid friction and how it's applied to architecture. Now, fluid friction is the wind effects against a building causing oscillation, vibrations, or even damage. Now, here is a demo talking about the wind effects against different types of walls. Now, here, as you can see, it's a very flat wall, and the wind is causing the wall to vibrate, causing stress. And as you can see, the wind is going back against the wall and coming back again. So it's causing like a barrier on the wind. Now, if I change this to a more aerodynamic shape, just like the one that you saw on the site. So the wind here is going around the building, causing less stress. And that is the fluid friction pertaining to architecture. Thank you very much. Toti for duties.